Welcome back to the deep dive. Today, we're tackling something pretty fascinating, generative diffusion models.
Right. And specifically, how this field, which is just exploding now with image generation and all that, sort of accidentally unified itself.
Exactly. It seemed like for years you had these three totally separate ways of thinking about generating data, different fields, different math.
Oh, it was chaos, frankly. You had people working on variational autoencoders, others on energy-based models, some coming from normalizing flows, different names, different equations.
But they kept landing on similar ideas.
Yeah, basically variations of the same core concept. So our mission today is to really distill the unifying principles from the source material we looked at.
We want to get beyond just the cool demos and understand the foundations, right? The math, the control, how they made them actually fast.
Precisely. We need to find that single thread that ties it all together.
Okay, so let's start with those three ancestral views, the perspectives that kind of independently stumbled onto diffusion.
Sounds good. And recognizing they are equivalent mathematically is maybe the biggest takeaway here, even if they sound miles apart initially.
So what's the first one?
Okay, first up is the variational view. This one has its roots firmly in variational autoencoders, VAEs.
Ah, okay.
And this path led pretty directly to DDPMs, Denoising Diffusion Probabilistic Models. That's probably the acronym most people heard first.
Right.
And the core idea here is framing generation as learning a denoising process. You start with your clean data. You have fixed, simple process to gradually add noise.
Step by step.
Step by step. And then the hard part, the learning part, is reversing that. Learning how to take that noisy mess and carefully remove the noise step by step to get back to the original data distribution.
So like running the noise process backwards. Got it. DDPMs from VAEs. What's number two?
Number two is the score-based view. This comes more from the world of energy-based models, EBMs.
Okay. Different angle.
Totally different perspective initially. Here, the focus isn't really on denoising steps, but on learning something called the score function.
Which is?
It's the gradient of the log probability density of the data. Think of it like a force field.
A force field. Okay, explain that.
Imagine your data lives on some complex manifold. At any point in space, even a noisy point far from the data, the score function tells you the direction of steepest descent on the log probability landscape.
So it points you back towards where the real data is likely to be.
Exactly. It's like a force field guiding any noisy sample back towards high probability regions, back towards the data manifold.
That's a really helpful visual. Okay. Variational denoising, score-based force field. What's the third lineage?
The third is the flow-based view. This one grew out of work on normalizing flows and things like neural ODEs.
Right, continuous models.
Precisely. They kind of threw out the discrete, noisy steps altogether, at least conceptually. Their idea was to learn a smooth, continuous, deterministic map.
No randomness in the generation path itself.
Not in the core formulation. It's a learned velocity field that transports points smoothly from a simple distribution, like pure Gaussian noise.
All the way to the complex data distribution you want to model, like a fluid flow.
Exactly like a fluid flow, a deterministic transport.
Okay, three very different starting points. But you said they converge. How does that happen? The source material points to continuous time, right?
Yes, that's the bridge. The continuous time formulation, often framed using stochastic differential equations, or SDEs. This score SDE framework basically unifies the discrete steps of the earlier model.
How so?
It casts the whole process, adding noise forward, removing it backward, as a differential equation evolving over continuous time.
So instead of discrete steps, it's a smooth evolution.
Right. And generating a new sample then just becomes solving the reverse time SDE. You start with noise at time t, and you integrate backwards towards time zero.
Okay, that makes sense for unifying the noisy approaches. What about the flow view, the deterministic one?
Well, if you take that reverse time SDE and you essentially remove the random diffusion term, the stochastic part,
We're left with just the drift.
you're left with just the drift term, which defines a deterministic ordinary differential equation, an ODE. That's the probability flow ODE, or PF-ODE.
Ah, so the deterministic flow is just the SDE without the noise injection during generation.
Exactly. It follows the same path on average. Yeah. And here's the real kicker, the aha moment the source highlights.
Yeah.
Whether you started thinking about denoising steps, variational, or score functions, score-based, or deterministic flows, flow-based, at the end of the day, you are always learning a single time-dependent vector field.
The velocity field.
The velocity field. That's the fundamental object. It's what transports the simple noise distribution to the complex data distribution. The math works out such that learning the denoiser, learning the score, or learning the flow velocity are all effectively learning this same underlying field.
So the arguments about what the network is predicting, noise, score, whatever, are kind of missing the point.
In a fundamental sense, yes. The training objective usually boils down to some form of weighted mean squared error, trying to get the network's output to match a specific target related to this velocity field.
Okay, so let's talk about that target. The source mentions 4 different ways to parameterize the network's output, 4 things it could be trained to predict.
That's right. And crucially, they are all mathematically equivalent. You can convert between them with some simple algebra.
What are the 4?
Okay, number 1, noise prediction. This is the classic DDPM approach. The network, epsilon phi, predicts the noise epsilon that was added to get to the current noisy state, $6.
Makes sense. Predict the noise, then subtract it, or a version of it.
Exactly. Number 2, clean prediction. Here, the network, 6 of hand phi, directly predicts its best guess of the original clean data, $6, given the noisy input, $6.
Okay, predicting the start point instead of the noise added.
Yep. Number 3, score prediction. The network predicts the score function, a nabla log px t t'other, that force field direction we talked about.
Right, the gradient.
And finally, number 4, velocity prediction. The network, Kiao, predicts the instantaneous velocity T-hats needed for that deterministic PF-ODE flow.
So noise, clean data, score, or velocity. But if they're all algebraically convertible, why choose one over the other? Is it just like academic preference or branding for a new paper?
That's a great question, and the monograph is pretty clear on this. The choice isn't about fundamentally changing what the model learns. It's mostly about practical stability during sampling.
Stability for the numerical solver.
Exactly. Remember, sampling involves solving that reverse SDE or ODE numerically. Sometimes the underlying dynamics can be mathematically stiff, meaning parts of the path change very rapidly, making it hard for simple numerical methods like Euler steps to follow accurately without taking tiny, tiny steps.
Okay.
Certain parameterizations, like velocity prediction, especially when combined with specific ways of scheduling the noise level over time, can result in a smoother, less stiff ODE to solve.
Ah, so it makes the integration easier, allowing for larger steps, faster sampling.
Precisely. It's about making life easier for the numerical solver, reducing what the source calls time-scale disparity, not about learning a fundamentally different or better generative process. The underlying velocity field being learned is the same.
That clears up a lot. It's an implementation detail, albeit an important one for performance.
The very important one, yeah.
Okay, let's shift gears. We understand the core mechanism, the unification, but raw generation isn't always useful. We need control, right? Generating an image of a specific thing, like a cat wearing a hat, based on a prompt time.
Absolutely. Control is key. And the way the source introduces this is through a really elegant application of Bayes' rule.
How does that work?
Well, you're interested in the conditional score, the direction to move, to make 6 cells look more like the theta, given the condition 2xl. Bayes' rule lets you decompose this.
Into what?
Into the unconditional score, the nabalog pxl, just the direction towards any plausible data, plus a term involving the gradient of a classifier, POJ, toward nabalog p.
Okay, so the direction you want is move towards data, plus move towards satisfying the condition C.
That's the intuition. It neatly separates the generative push from the conditional steering.
So how was this first used?
The early approach was called classifier guidance, or CG. It took this decomposition literally. You'd train your main diffusion model for the unconditional score.
Just generating anything.
Right. And then you'd also train a separate classifier model, CSTD, that could look at a noisy intermediate sample, $6, and predict the probability of the condition CST.
And you'd use the gradient from that classifier to steer the generation.
Exactly. You'd add the gradient from the classifier nabla log to the unconditional score during sampling. It worked, but needing that separate classifier was cumbersome.
Okay, so what replaced it? I assume that's where classifier-free guidance, CFG, comes in.
Precisely. CFG is the modern standard, much more elegant and often more effective. It gets rid of the need for that external classifier. The trick is to train a single diffusion model to predict both the conditional score and the unconditional score. Usually this is done by randomly dropping the conditioning information city-holler during some percentage of the training steps.
So sometimes it sees the prompt, sometimes it doesn't.
Right. So the model learns the nabla log pxc when a Zollers is provided, and the nabla log pxc when the Zollers is dropped, or replaced with a generic null token.
And then at inference time.
At inference time, you run the model twice per step, once conditionally, once unconditionally. Then you extrapolate. You take the conditional prediction and push it further away from the unconditional one.
So you calculate conditional, unconditional to get the pure guidance direction, scale that up, and add it back to the conditional estimate.
Basically, yes.
Yeah.
It's a simple interpolation. Guided, unconditional, plus guidance scale, conditional, unconditional. This effectively amplifies the condition's influence. It's efficient and works remarkably well.
Makes sense. Okay, that covers predictive prompts. But what about aligning generation with fuzzier things, like human preferences, making an image more beautiful or more creative? That seems harder than just matching text.
Yeah, that's the alignment challenge. The traditional path here, borrowed from large language models, involved reinforcement learning from human feedback, RLHF.
Which usually involves training a separate reward model.
Exactly. You collect human preference data, which image do you like better, train a reward model to predict those preferences, and then use RL to fine-tune the diffusion model to maximize the predicted reward.
But RL can be tricky.
Notoriously unstable, complex to implement, sensitive to hyperparameters, plus you're relying on that intermediate reward model being accurate.
So is there a better way suggested in the source?
Yes, thankfully. The monograph points to Diffusion DPO, which stands for Direct Preference Optimization. It's a much cleaner approach.
Direct? How so?
DPO skips the explicit reward model and the unstable RL training loop entirely. Instead, it derives a loss function directly from the human preference data, the pairs of winner and loser samples.
Okay.
The loss function essentially encourages the diffusion model policy to increase the relative likelihood of the preferred winner samples compared to the less preferred loser ones, judged against a baseline reference model.
So you're directly tweaking the generator's probabilities based on which outputs people liked better.
Exactly. You're teaching the generator make outputs that look more like this preferred one and less like that rejected one directly, without needing to first model why humans prefer it. It's more direct, more stable.
That sounds way more robust. Okay, great. Foundation, unification, control, alignment. The last big hurdle is speed.
Ah, yes, the Achilles heel.
Standard DDPM sampling you mentioned takes hundreds, maybe thousands of sequential steps. Way too slow for many applications.
Definitely the critical limitation. The source material breaks down acceleration techniques into roughly two camps.
What's the first camp?
Training-free acceleration. This is all about using smarter math, better numerical solvers to approximate the generation path, the reverse SDE or PF-ODE, more accurately with fewer steps.
So no retraining the model, just running it differently.
Exactly. Early examples include things like DDIM, Denoising Diffusion Implicit Models, which provided a deterministic update rule that allowed skipping steps. You could view DDIM as a kind of first-order solver for the PF-ODE.
But first order isn't always accurate enough for big steps, right?
Right. For really fast sampling, like 10, 20 steps instead of hundreds, you need more sophisticated solvers. This led to things like the DPM-Solver family.
What do they do differently?
They use techniques from numerical differential equations, like higher-order methods, think Runge-Kutta style, but adapted, and exponential integrators, which are particularly good at handling the structure of the diffusion ODEs. They get much better accuracy per step.
Allowing for high fidelity with maybe just 10, 15 steps, you said?
Yeah, sometimes even fewer, depending on the model and the desired quality. It was a huge leap in usability.
Okay, that's training-free solvers. What's the other camp?
The second camp is training-based acceleration. Here, the idea is to actually train a new model, a student, specifically designed to be fast, often by learning from a slow, powerful teacher model.
So you're baking the speed into the model itself.
Exactly. One major approach here is progressive distillation, PD.
Distillation? Like compressing knowledge?
Kind of. You start with your slow teacher model that takes, say, 1,000 steps. You train a student model to replicate the output of 2 teacher steps in just 1 student step.
Ah, so the student learns to jump ahead.
Right. Once that student is trained, it becomes the new teacher, not taking 500 steps. You repeat the process, train a new student to do 2 of its steps in 1. You progressively halve the number of steps required in each round of distillation.
Until you get down to maybe 4, 2, or even 1 step.
Potentially, yes.
Yeah.
You trade some training time for much faster inference.
Okay, that makes sense. What's the other main training-based approach? You mentioned learning from scratch.
Yeah, that leads to consistency models, CM. This is framed almost as a new standalone generative modeling principle, though related. The key idea is that they are trained to map any point along the noisy trajectory directly back to the origin, the clean data.
Directly back, not just 1 step back.
Directly back to the beginning of the trajectory. They enforce a consistency property. The output should be the same regardless of which point 6L evolve along a single trajectory you start from.
How does that help with speed?
Because the model learns the entire flow map solution, TSIT, in a way. It doesn't need to simulate the intermediate steps during inference. You can give it noise too, and ideally get a good estimate of $6 in a single forward pass, or maybe just a few refinement steps.
So CMs learn the whole path solution directly, while PD learns to take bigger, discrete jumps along the path.
That's a good way to think about it. CMs enforce this self-consistency across time, allowing potentially very few step generation, even trained from scratch without needing a pre-trained teacher model, though distillation can also be used to train them.
Okay, so to recap speed, either use a smarter solver on the original model, training free, or train a new model via distillation or consistency training to be inherently faster, training-based.
You got it. That covers the journey pretty well. From those messy, disparate origins, VAEs, EBMs, flows to this unified view through differential equations.
Then getting control with guidance like CFG and alignment with DPO.
And finally tackling the speed issue with better solvers and techniques like PD and CM.
The unification really brings a lot of clarity. It feels less like magic now and more like principle engineering.
Definitely.
So what's the final provocative thought the source leaves us with? Where might this be heading?
It draws a really interesting connection to the mathematical field of optimal transport, or OT.
Okay, how does that relate?
Well, OT is all about finding the most efficient way to move probability mass from one distribution like noise to another, like data. The deterministic PF-ODE, learned by diffusion models, is a transport map. It moves noise to data. And the way it's learned, minimizing certain losses, often relates to minimizing a kind of kinetic energy, which sounds like some formulations of OT, like the Benamou-Brunier dynamic formulation. The catch, as the monograph points out, is that the transport map learned by current diffusion models is generally not the true, provably optimal transport map in the strict mathematical sense. It finds a path, often a good one, but not necessarily the absolute most efficient one that minimizes the total transport cost.
Ah, I see. So the flow it learns works, but it might not be the straightest, lowest cost path mathematically possible between noise and data.
Exactly. It's a valid transport, but likely not the optimal one.
So the final thought is, could we design future diffusion models differently? Could we explicitly constrain them or train them in a way that forces them to find that true optimal transport map?
That's the question. If we could, it might lead to even more efficient sampling, perhaps better generalization or a deeper theoretical understanding. Finding that truly optimal path remains an open challenge.
A fascinating possibility. Could there be a fundamentally more efficient way to generate data that we haven't unlocked yet?
Perhaps. It's definitely something for researchers and for you listening to think about.
A perfect place to leave it. Thanks for that deep dive. We'll see you next time.